I'm handing out an electronegativity table, which we will use more on Friday, but we will use it a tiny bit today. So I want to make sure you do have that. You have a quiz on Friday. It will be on naming. You have to have all of those polyatomic anions and the naming rules down. So you're welcome to come to question hours right before that. I have question hours 10 to 11:30 on Friday, or even better, you can come to question hours tomorrow morning or go to the CLC like Chris said earlier. So what is a binary covalent, otherwise known as molecular? You'll hear that, and that's what it is on your naming, your decision tree that I handed out on Monday. Compound, so a covalent or molecular compound, they mean the same thing. Does anybody remember what I said a covalent compound would consist of as opposed to an ionic compound? Two nonmetals, at least two nonmetals. And in this case, because we're talking about binary covalent compounds, it will be two nonmetals. You're not going to have to name any covalent compound that has more than two elements in it. That can get very complicated, as if you go onto organic chemistry, you will learn. But we're just going to do two elements, both nonmetals or metalloids. And what does covalent mean? What is, they share electrons. Okay, so we're not going to have ions. These elements that are going to be bonding, they're going to be sharing their electrons instead of being attracted to each other because they've already lost their named electrons and they have positive and negative charges. Our naming system is relatively simple and goes as follows. You have AX, BY. A and B are your two elements, and X and Y are their subscripts. So how many of each there are? A will have no suffix change. And only a numeric prefix if X is greater than 1. So if there's more than one of A, it will have a numeric prefix. If there's only one, it will not. And we will go over those numeric prefixes for right now. Let's just write down the rules. So no suffix change and only no numeric prefixes if X is greater than 1. B will always end in "ide" and always has a numeric prefix. So you're going to have to know the numeric prefixes. This will not be on the quiz this week, but it will be on the test because we're learning it this week, right? So everything on the quiz is from last week. So the numeric prefixes that you have to know will be the ones for 1, 2, 3, 4, 5, and 6. You can go much higher than that, but in this case, in this class, you only have to know 1 through 6. My numeric prefix for 1, so if I have 1 of A or 1 of B, it's going to be mono. If I have 2, it's going to be di. What do you think 3 is? Tri. 4 is a little odd. It's tetra. But if you remember, so Tetris is named Tetris because each of the blocks, each of the shapes has 4 square blocks in it. So that's why it's called Tetris. Tetra means 4. So tetra. What do you think 5 is? Based on geometry? Penta, as in a pentagon. And 6? What is a 6-sided figure in geometry? Hexa. There we go. Okay, mono, di, tri, tetra, penta, and hexa. Make sure you have all these down, and then I'll describe how this applies to the rules we just wrote. Through 8, septa and octa. But in my class, you only have to know through 6. All right. For example, you know what this is. What is this? Just from your knowledge. Carbon dioxide, which is a problem right now for climate change. And carbon dioxide follows this, that name follows these rules because the first element is carbon. It has no change in its suffix, just stays carbon. And because there's only one carbon, you don't give it a numeric prefix. The second element always ends in "ide," oxide, and it always has a numeric prefix, dioxide. How about this? Carbon monoxide. Both of these are things you should not breathe in a lot of, which is why we know these, because we're warned against them in terms of fire and exhaust. And once again, this follows those rules. Carbon, there's only one, no change in the suffix. Oxide, because the second element always ends in "ide," and it always has a numeric prefix. You'll notice that mono, I left out an O because it would be like mono-oxide, but for the prefixes with oxide, you could take out that extra vowel, so it's just monoxide. Same thing with like pentoxide, so you would just take out that A. So the only ones where you don't take out that extra vowel for oxide is di and tri. So dioxide and trioxide. The rest, it's just one vowel there. So how about this? What is this? What's the first part? Let's just deal with this right here. Diphosphorus, because if this subscript is greater than 1, if there's more than 1, then you have the numeric prefix. So it's diphosphorus, and the second part, pentoxide. This what's the first part of this name? Carbon. And tetrafluoride. And finally, using this naming system, common name is water, dihydrogen monoxide. So I don't know if you've seen those things on the internet that are like, make fun of people who are scared of chemical names, and they're like, dihydrogen is in all of your food, everything you eat and drink. And it's like, yes, it's water. So that's why it's good to know your chemicals and know what's dangerous and know what's not. Dihydrogen monoxide. This, by the way, is the only compound in this class that we starts with an H, but we don't name it as an acid. All right? But you know what that is. That's water. Water can act as an acid, but you'll deal with that later in another class. I would like you to practice PCl5, S2O4, and C3H6.
Say you still play this fine.
No, I love playing. Alrighty, what's the first one? Phosphorus pentachloride. Because there's only one phosphorus, so it does not have a numeric prefix. This is much simpler than ionic and acidic naming. Would you agree? Yes. This is why I save it to last. So what's the second? Disulfur. Tetroxide. Yes. Take out that extra vowel so it sounds nice and smooth. Tetroxide. And then the last one. Tricarbon hexahydride. Hydride. Yeah, so you take the first syllable, chloride, oxide, hydride. Questions? We good? Know this for the test next week. Let's talk about how to draw these structures. There are many ways to draw molecules and atoms. We're going to use the system that is called the Lewis dot structure or the electron dot structure. So if I say Lewis structure, dot structure, I'm talking about the same thing. I'm talking about what we're going to go over. Lewis or electron dot structures of neutral atoms. We'll put them into molecules later, and we'll do ions later as well. Neutral atoms. This is when you look at the periodic table and you count across the periodic table for how many electrons you have. Before they gain or lose electrons to fill out their octet, you want to make sure that we're drawing the neutral atoms. You only have to know how to draw these for the first 3 rows, because starting with n equals 4, you have the transition metals and things get complicated in terms of drawing out these kind of structures. So we're just going to deal with rows 1 through 3. I'm going to start with row 2 because it's a little more straightforward, and then I'll go back and complete row 1. So 1, 2, and 3. So how many valence electrons does neutral lithium have? 1. It's in 1A. It has 1 electron. You put a dot on one side. So you consider 4 sides, 1, 2, 3, 4 of the symbol. I don't care where you start putting this dot. You can put it on the top, bottom, left, just 1 dot, okay? How many electrons does beryllium have? 2. You can put the second dot on any of the other 3 sides, but it has to be on a different side. Because as we add electrons to these orbitals, they kind of want to space out. Just like if you were adding students into a dorm, you would try to make sure as many students had singles as possible before you started putting them into double rooms, okay? In a perfect world, we would all have single rooms, but that doesn't happen. So, once again, electrons, they want to be spaced out, and then they start pairing up. So how about boron? How many valence electrons? 3. 1, 2, 3. Carbon? 4. 1, 2, 3, 4. We have now taken up all of the spaces. We're going to have to start pairing up the electrons. So nitrogen is going to have 5. 1, 2, 3, and at 4, and then I'm going to add another electron in a pair. Any side, as long as there are 3 lone electrons and 1 pair. Oxygen is going to 1, 2, 3, 4, 5, 6. So it's going to have 2 pairs and 2 lone electrons. Fluorine, it has 7, so it's going to have just 1 electron by itself. And finally, neon has a full octet. It's totally happy. It has all paired electrons. This denotes a full octet, a full valence shell. So I'm going to go back to row 1. How many valence electrons does hydrogen have? 1. It's going to look very similar to lithium. However, helium is a little weird because how many electrons can go into the valence shell of helium? Just 2. Because as you count across, it's just hydrogen and helium. So helium, when we draw that, it's just going to be 2 electrons on the same side to denote that there's only room for 2 and it's full up. Okay, so helium's a little weird. Helium is different from beryllium because helium has 2 electrons and it has a full valence shell. And beryllium has 2 valence electrons, but that has a double shell. So these Lewis and electron dot structures only concern the valence electrons, the outermost orbital shell. given that, what do you think sodium will look like? Just like lithium. And magnesium is going to look just like beryllium, and so on. So as you go across the table, row 3 looks exactly like row 2 because they have the same number of valence electrons as the one directly above it. Make sure you actually make it clear that they're dots. Don't do like, if I see like just like a tiny like little like faint pencil mark, I'm not going to know whether that's a dot or not. So actually make it clear that you're putting in those valence electrons. Questions on this? That's one. It's just a big one, just a smudge. Yeah, that's. It should just look just like beryllium, but with a different symbol. Alrighty. Once again, it does not matter which side you start on, as long as you space out the electrons until you have four sides with one electron. Then you start putting them into pairs.
Really quickly, can you say
Yeah, so hydrogen, just like lithium and sodium, has one valence electron. However, helium has two valence electrons, but that's as many as that orbital can hold. Like, so the first valence shell can only hold 2, and the next 2 valence shell can hold 8 and 8. So to denote that we've filled up that valence shell, we put those electrons on the same side. Whereas beryllium and magnesium both have 2 valence electrons, but they still have a whole bunch of room. So these electrons are gonna separate. Okay. Let's draw the Lewis or electron dot structures of monatomic ions. Remember me what monatomic ions are? It doesn't have one charge. I mean, usually they do, but it has one element, yes. So what are some examples of monatomic ions? Oxide, that's a monatomic anion. What's a monatomic cation? That's polyatomic, it has 2 elements in it. What's an example of a monatomic cation? That's a compound. One element that has a charge. Sodium is a monatomic cation because it is a positive ion and it's only one element. Okay? Know what these are. Sodium. This is neutral sodium. This is how we drew it before, but we want to make it into the sodium ion. What does it do to become the sodium ion? It loses that valence electron. So you're going to lose one electron, and it's going to become Na+. Because we're dealing with the valence shell, Sodium's outermost shell now has no valence electrons, so we draw just Na+. You got rid of that valence electron, just Na+. An anion will be slightly different. For example, if we have Cl, which is chlorine, to become chloride, what is it going to do? Add an electron. So now it's going to have a full octet and a negative charge. And the way we draw that is it has a full octet, brackets, and a negative charge. That negative charge can go on either side, can go here or here. But it's so when I ask you to draw this ion, there will be a point for the full octet, a point for the brackets, and a point for the charge. Let's talk about what happens if you gain or lose more than 2 electrons. I mean, more than 1 electron. For example, Mg has 2 electrons when it's neutral. When it forms its ion, what is it going to do? Lose 2 electrons. So once again, magnesium doesn't want those extra 2 electrons. That's like having 2 employees on a big floor. It's really energy inefficient. It's going to get rid of those 2 guys. And so it's going to lose 2 electrons and become Mg+, because once again, it lost all of its valence electrons. What does sulfur do to become sulfide? Gains 2. So how many electrons is sulfide going to have? It's going to have the full octet because that's the whole reason it gained those 2 electrons. Once again, a charge and a 2-. So cations, no valence electrons, no bracket. Anions, full octet, bracket. And you must give the charge on both. And that charge should be outside of the bracket. What that bracket is saying is that I've got this ion, and that charge is being shared it's like a ball of charge. It's shared around the whole ion. It's not at any specific place on that ion. Yeah. Yes. Thank you. Here you go. Questions? Now we're going to put these together to create Lewis structures of ionic compounds. So these are just ions. We're going to put them together to form compounds. Can I move on? Oh yeah, Jacob. On the outside, yes. Dot structures of ionic compounds. What is the lithium ion going to look like? Based on what you just learned, look at your notes. What is the lithium ion going to look like? I'm talking about the ion. The neutral lithium has 1 dot. Okay, be clear on what the difference between a neutral atom and an ion is. The neutral atom is how many electrons it starts with, and then it's going to gain and lose those electrons to have a full octet, to have a full valence shell. and that's when it has the charge. Okay, so neutral lithium will be Li with a dot. Lithium ion will be Li plus, because it loses an electron to become Li plus. So you have Li plus. What is the chloride ion going to look like? Cl minus, but what are we going to include in this dot structure in addition to the Cl and the minus? Full octet and brackets. Yeah, okay, I'll draw it out. So lithium starts as Li with a dot. That's neutral lithium. But lithium doesn't want that electron. So what is it going to do? Get rid of it, and it becomes Li plus. Cl starts out with 7 electrons. What does it want? It gains 1, so now you have a full octet, but now because now you have 1 more electron than you have protons, it's going to have a minus charge and brackets. Does everybody see how I did that? So these two compounds that have lost or gained electrons are going to be attracted to each other because that's what ions do. Opposite charges attract. That is lithium chloride drawn out as a Lewis dot structure. You might also have more than one of either element. For example, Na2S. You put basically the odd man out in the middle, right? Because you don't want two positive charges next to each other. So the sulfide, which is going to be a negative ion, is going to be in the middle, and you're going to put the sodiums on either side. So what is sulfide going to look like? It's going to be S, 2 minus, and what do we have to put? How many electrons does it have once it gains those 2 electrons? Full octet. And then what else are we missing? Brackets. What are the sodiums going to look like? Na plus. And you're going to put them on either side because like charges want to be separated and they like hanging out on either side of this big negative charge. Questions on that? It might be the other way around where you only have 1 positive ion, but you have 2 negative ions. For example, MgCl2. What does the magnesium ion look like? That's the neutral magnesium. Neutral magnesium has 2 dots. It's going to lose those 2 dots to become Mg2+. What does chloride look like? Not chlorine, chloride, the ion. Full octet, brackets, and a minus charge. And because we don't want 2 negative charges next to each other, the other chloride is going to go on the other side. So you space out the ions so they're not next to each other. So if I gave you, if I said, just wrote out, give the ionic Lewis structure of magnesium chloride, first you would have to figure out what my magnesium chloride was. You'd have to write out the ionic compound, the formula. Then, because it would need to be charged balanced, then you would see you would have 1 magnesium and 2 Cl minuses. So you would draw it out this way. Okay, so figure out what the ionic compound is, make sure it's charge balanced. Based on that, draw out your Lewis structure.
So in this last one, magnesium giving an electron on chlorine.
I got the same exact question yesterday in lecture, and I don't like saying that magnesium gives its electron, because that's not always the case. Yes, sometimes magnesium and chlorine will come together and they'll just exchange electrons directly. But that's not always the case. Sometimes chlorine's over here and it undergoes a reaction where it gains an electron. and then magnesium is over here, and it loses 2 electrons. Then they find each other and they attract each other. So I don't like saying it's a direct transfer from this ion to these ions. They have lost or gained electrons in whatever manner, and then the attraction causes them to form a compound.
Yeah, because they're not sharing.
They're not sharing, so they've already exchanged electrons, but it's not always like directly with each other. So I don't like saying just like magnesium gives its electrons away to the chlorides.
Why does the chloride have to charge? Is it stable?
Well, yes, that's the whole reason it has a charge, right? Because neutral chlorine has 7 electrons. It doesn't like being neutral because it doesn't like having 7 electrons. So it gains that electron to be stable and has a negative charge. So just because it has a charge doesn't mean it's unstable. It actually makes it more stable because it likes to have that full octet. So these elements actually become more stable when they gain or lose electrons because they want to fill out their octet. But then they attract other opposite charges. Is that clear? Okay. Finally, you might have something like AlCl3. And in this case, just space the chlorines kind of around the aluminum. So like I might have one chloride here. I might have another chloride here. And one down here. Just make it clear to me, like I don't really care, you could switch these, but just make it clear that you're not bunching all the like charges together, okay? Just kind of space them out around the central charge. Questions on this? You doing okay? Let's talk about covalent Lewis dot structures. Remind me, what is a covalent bond? Shared electrons. So are we going to have ions? No. So if it's an ionic compound, you're going to draw it like this. If it's a covalent compound, we have another system. If we want to draw Cl2, there's an order of steps that we go through. So remember, Cl2 is a covalent compound. It's a pure element. It has a bond between Cl and Cl. It's not the ion, right? Because that would be Cl minus. So first, we're going to count number of valence electrons. We're going to count the total. And once again, Lewis structures only deal with valence electrons. How many valence electrons do we have in this structure? 14. Each chlorine has 7, because it's neutral, has 7 electrons. You add those together, it has 14. 14 valence electrons. So my second step is I'm going to place electron pairs between atoms. That's forming the bond. One bond is 2 electron pairs, and the most important thing in forming a molecule is that you actually have bonds. So since in this case we only have 2 atoms, we're just going to place a pair right there. We have our bond. Our third step is place all other electrons in pairs around the atoms and they want an octet. Okay, never ever in this class add a lone electron. Add lone pairs of electrons. Pairs of electrons. Do not add a single electron. So I'm going to do Cl. Oh, I already used up 2 of my electrons, so 2. And then I'm just going to start other electrons. And they want an octet. So I started with 2. So 4, 6, 8, 10, 12, 14. That's as many electrons as I can put in because that's all we have. That's all of our valence electrons. Are they happy? Yes, because these 2 electrons count for both. They are shared, so they count for both octets. So this chlorine has 8 and this chlorine has 8. They're both happy. We have our structure. The last thing is, and I want you to do this, don't leave it as an electron pair. Replace pair with a bond. And what I mean by that is you draw a line, but you leave the lone pairs hanging out. Okay? So you just take the bond pair and turn it into a line to denote that that is a bond. Does anybody have any questions? I would say your 5th step is double check that you have the right number of valence electrons and that you have no electrons, single electrons floating around. You always want them in pairs, and you want to make sure that you used exactly 14 electrons. So always double check at the end. Let's move on to a different compound. O2. How many valence electrons do we have? 12. So 2 times 6 equals 12 valence electrons, right? Because oxygen is in group 6A. It has 6 valence electrons. So 2 of them means 12. So let's first draw our atoms. What's my first step? I have to put the electron pair in the bond, right? Between the atoms. Now I'm going to add the rest of the 12 electrons around in pairs. So I have 2, 4, 6, 8, 10, 12. Okay, I'm done. Are we happy? No. This oxygen only has 6. It wants a full octet. So when this oxygen sees that this oxygen is dissatisfied, it's going to share an extra lone pair. If you run out of electrons to give everyone a full octet, put electrons into bonds. So I'm going to take this and move it here, so it's going to look like so 2 lone pairs, and they're sharing 4. So this contributes to both octets. Are we happy now? Yes. What's our last step? Yeah, so in this case, since we have a double bond, it's going to be 2 bonds and then lone pairs. And I tend to space out my lone pairs, but if you just left it like top and side, that's fine. I'm just, once you get to 110, you'll be used to spacing out your lone pairs at that angle. Questions? How about carbon monoxide? How many valence electrons do we have? 10. Carbon has how many valence electrons? Oxygen has 6, so that's 10 valence electrons. CO, we're going to start with our electrons in there. So 2, 4, 6, 8, 10. Are we happy? No. Carbon only has 4. So let's put one of those lone pairs into the bond. Is carbon happy? No, because it still only has 6. 2, 4, and 6, but oxygen has 2, 4, 6, 8. So what's oxygen going to do? Put another electron pair into that bond. So now we have C. Is everyone happy now? Yes, because they're sharing these 6, and then each of them has a lone pair. That is a triple bond. You'll notice that the fewer electrons you have, the more bonds you have to make. Because we started at 14, and they only had to have one bond. We went to a diatomic compound that had 12 valence electrons, and they had to share 4 for a double bond. And then we went down to 10, and they had to have a triple bond. The least electrons you have, the more you have to share.
So this works out because
They both have a full octet. And what I mean by that is that carbon has a lone pair and shares with 6 here. So that's 6 plus 2 is 8. Same with oxygen, also shares those 6. 6 plus 2 is 8. These molecules won't always be symmetrical. Sometimes one atom will have more on one side and one will have less. Let's draw, so we did monatomic Lewis structures. Diatomic Lewis structures where you just have 2 atoms. Let's do multi-atomic Lewis structures. For these, there's a couple of rules. One, H can only make one bond. So it is never the central atom. Can anyone tell me why it can only make one bond? It's not because it only has one electron. Where is it on the periodic table? It's in the first row, which, what does that say about it? Yeah, the valence shell can only have 2 electrons. The first valence shell can only have 2 electrons. So if hydrogen makes one bond, guess what? It has 2 electrons. It filled its valence shell. It can't do anything more. So hydrogen will only have one bond, and it will never have lone pairs. The second rule is that the least electronegative element besides H, because we know that H can't be in the center, is central. So even if your even if a hydrogen is less electronegative than another atom, it still can't be in the center. So everything, so the least electronegative atom besides hydrogen has to be in the center. So that's why I gave you those negativity charts. So the way you read the negativity chart, electronegativity chart, is higher number is higher electronegativity, lower number is lower electronegativity. Okay, so let's go into drawing H2O. What's going to be the central atom? Oxygen, because hydrogen can't be the central atom. How many valence electrons do we have? Well, how many total electrons do we have to do the fluid structure? 8, because we have 2 hydrogens, each of those have 1. And then oxygen has 6, and so we have 8 valence electrons. What's my first step? Bonds. 1, 2, 1, 2. Okay, so in this case, you have to have bonds between each set of atoms. We have 4 electrons left. Where am I going to put them? On the oxygen. I can't, hydrogen already has 2 electrons. It can't have any more, so it's just gonna go on the oxygen. Are the hydrogens happy? Yes, hydrogen is the only thing that's going to bond and be happy with only 2 electrons. And is oxygen happy? Yes, because it has 8, it has a full octet. And then you just draw your bonds. CCl4, what's going to be the central atom? Carbon. Chlorine is much more electronegative than carbon if you look at your electronegativity chart. So you're going to put carbon in the center and all the chlorines are going to go around it. How many valence electrons do we have? We have more than that because we have 4 chlorines. How many electrons does the carbon have? Valence electrons does the carbon have? How many electrons does each of the chlorines have? So you have to account for all of them. So 4 plus 4 times 7 is 32. What do I do with the first electrons? Bonds, put them in the bonds. So 2, 4, 6, 8. Am I going to put anything else on carbon? No. So I'm going to just put the rest of the electrons around the chlorines. 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Is everyone good? Yep. Once again, make it clear that these are dots and not just random pencil marks. That is your carbon tetrachloride compound. Let's do one more. How many valence electrons are in CO2? 16, because oxygen is 2 times 12 for that, and then 4 for the carbon. Sorry, 2 times 6, which equals 12, plus 4 for the carbon, which gives you 16. So let's draw out our, well, first of all, what atom is going to go in the center? C. Let's put in our bonds. So that's 2, 4, 6, 8, 10, 2, 4, 6, 8, 10, 12, 14, 16. Is everyone good? The carbon is not happy. Why is the carbon not happy? It has 4. So what are we going to do? Take a lone pair from each side. Now is carbon good? Yep. It has 4 electrons here, 4 electrons here. These guys are good. So we have 2 double bonds. Oops. You could have started putting like giving carbon the full, adding the lone pairs to carbon and then to 1 oxygen. You still would have had to move everything around so that it had 2 double bonds. In general, except for in a diatomic molecule, where there's only 2 atoms, the rule is elements form as many bonds as the number of electrons missing from their octet. Based on this, how many bonds is chlorine gonna form? One. Chlorine has 7 electrons. It wants to have a full octet. It's going to form 1 bond. That's going to help it fill out the full octet. So chlorine, 1 bond. Oxygen, usually 2. Nitrogen, 3. It has 5 electrons. It wants to form 3. And what about carbon? 4. Carbon, we saw that carbon monoxide, it had a triple bond with oxygen. That's the case. We just, because it's a diatomic molecule, we don't have like a quadruple bond. So in that case, they each had 3 bonds. But in general, carbon has 4 bonds. Carbon is a electron sharer. It wants to share. It wants to make as many bonds as possible. Because remember what I said electronegativity is? Does anybody remember from a couple weeks ago what electronegativity is? It's tendency to gain electrons or take electrons or to pull electrons towards itself. Chlorine is very electronegative. It wants to have as many electrons to itself as possible, and it's only going to try to share just through 1 bond. Carbon is not very electronegative. It's like, I'll share. I don't like really care that much whether I'm getting all of these electrons. So that's why it forms 4 bonds. It can share. The more electronegative something is, the less of a sharer it is. All right? The greedier it is for electrons.
Sorry, one more time. Electronegativity was the tendency to gain?
To pull electrons towards itself. And sometimes that means pulling an electron like totally towards itself, like chlorine sometimes does form the chloride ion because it's like, give me that electron. greediness for electrons. Questions?
More electronegativity, the less.
It wants to share. So the less bonds it's going to form. So if you look at the electronegativity of these elements, it goes, this is the highest, this is the lowest. We'll do more with the electronegativity on Friday, so definitely bring that back. Let's do a worksheet.